Well, good morning, everyone. Thanks for coming. So it's a real pleasure and honor to introduce Paul, who will be familiar to many of you. Professor Paul Taylor, who is now an emeritus professor here at UWA. And you'll know that Paul works across a huge range of topics, from sort of wave physics, wave statistics. The term new wave was sort of coined and partly invented by Paul on sort of wave structure interactions. Paul looks at loads on fixed sort of jackets, monopiles, which is the talk today. Green water overtopping, looking at floaters, looking at dynamics of wave energy converters. I guess one of perhaps favorite hobbies of Paul is sort of rummaging in data. And he's come up with really elegant, sophisticated ways of analyzing lab and field data, including the sort of phase-based harmonic separation methods that will be familiar to many of you. So Paul hasn't spent all his time at UWA, even though it feels like it, because he's been working with us for a long time. So he started in Cambridge, and then he had a very distinguished career in Shell, then moved on to Oxford, and since then has also held visiting professorial chairs at NUS, now also in Plymouth. And it's just, real pleasure that Paul is still part of the group and mentors many of us. So thank you, Paul, for giving this talk and coming to see us. Look forward to it.
My pleasure. Thank you very much, Anna. I guess I've been doing safety-related research throughout my entire career. I did my PhD in Cambridge and then joined Shell and spent the first half of my time in Shell trying to demolish platforms by blowing them up. Then the second half of my career trying to knock them over with giant waves. And I've been interested in giant waves ever since. I remember being a small boy down in Cornwall on holiday when I was about 7, being absolutely fascinated by breaking waves on the beach. This is after I built my sandcastle, of course. And now, through most of my career, people pay me to think about waves. So what more could you want? Your hobby and your job is combined. Okay, so what I want to talk about is forces on single structures. You're all familiar with the Morrison equation, which was defined in the early 1960s. Actually, do you know the story of Morrison? Morrison was not a PhD student, he was a master's student who did a summer project. And his supervisors invented the Morrison equation, but being charitable, they put his name first on the paper. So it is his one and only paper. He then went off into Wall Street and made lots of money. So he didn't stay in offshore engineering for very long. But the Morrison equation has 2 terms in it. It has a drag term, and we're all interested in peak velocities and the loads on structures, on drag-dominated structures like space frames. But there's another term, which is called the inertia term, which actually turns out to be the dominant term for monopiles. It's not something we usually think about in sort of classical offshore engineering, but it does turn out to be a really interesting and significant term for the monopile problem. So I'm interested in forces on single columns that in these days generally support offshore wind turbines. This is work that I did with Tim Tang from Oxford, and also you'll see some experiments that some beautiful experiments that Jan has done. I'll talk about those at the end, and some contacts in Oxford and Bath. Okay, so there's a project that I'm associated with, which is run by Jun Zhang in Bath with Tom Adcock, and some connections to Strathclyde in the UK. This is the so-called Sea Swallows project. All good projects should have an acronym. So severe storm wave loads on offshore wind turbines, which is almost equivalent to sea swallows. So there's just a couple of stills here. On the left, monopile structures being hit by big waves, lots of splashing, lots of forces. And then the right-hand side, 3 turbines. Actually, if you look very closely, they're on mini jackets, not monopiles, but we'll pass over that. It was the only picture I could find of a big breaking wave. So we're interested in those sort of loads. And I should say, I'm interested because, as far as I'm aware, there has been no collapse of any offshore wind turbine due to wave overload. And you think how many fixed turbines there are in the world now. That, to my mind, means they're massively over-designed. Now, whether they're designed by dynamics or fatigue or the geotech side, but certainly the wave loads are clearly not a design question, or at least they're designed out. There's money being wasted, and that's clearly not a good thing in renewables. Okay, so the background, you can see a picture on the left is a forced time history as a big wave group goes past a single column. And the blue curve, which you can see there, is just the normal linear inertia term from the Morrison equation with a picture on the top right. But that's not quite everything that one wants. There's nonlinear terms, nonlinear forcing, and we're interested in a process which is faster than CFD. I mean, the classical problem for CFD to solve is flow around a cylinder, and it'll do a very good job these days. But the problem is you need large amounts of computing and you need to be patient. So what I'm interested in is coming up with a much faster recipe. Why do the higher order terms matter? Well, they matter because of structural dynamics. So if you look at the picture on the left, the linear force time history in blue and the nonlinear terms add on. They make the transitions faster, they make the peaks a bit higher. They don't look on the left as though they do that much, but if you look at the frequency content on the right-hand side plot, that's a force spectrum as a function of frequency, you can see the wave peak well below the shaded area. The shaded area is where the resonant frequency of the turbine columns are, typically somewhere between 2 and maybe 4 or 5 FP. And you can see some resonance, or you can see some spikes in there. Those are the nonlinear terms that come through from the Morrison inertia term when you do the calculations properly, which is what we're trying to do. So you're worried about fatigue as well as extreme environmental overload for columns. At least you should be. If you have a relatively low damped dynamic response, then the loading could be in brown here and the structural dynamic response in blue. So you can see the vibration induced by the wave going past the structure. And if you go back 30 odd years in classical offshore engineering for big concrete platforms off Norway, this phenomenon is called ringing. And there was a big, various lots of studies done, including the most important paper there. But the key thing to understand is that for the fixed offshore wind problem, turbines and turbine structures have very little structural damping. So if you hit them, they vibrate for a while, and that's clearly going to use up some of your fatigue life in the steel work. And there's evidence from oil and gas from a long time ago that the best models, best analytical models for ringing responses are inadequate. And that's been the case for a long time now. Okay, so the aim is to take a crude linear representation of the free surface and transform it into as close to fully nonlinear force time history as we can get. And particularly, we want to do this quickly, and we want to do it accurately. We don't want to do CFD, because CFD takes hours on a big supercomputer. We want a force transformation which will give me the answer essentially within 0 computational time. Okay, so if you go back in the literature to 1995, there's a paper written by Fultonson, Newman, and Vigna, 3 greats of hydrodynamics of that sort of era, where they had identified not only the Morrison inertia loading, but an extra local forcing close to the free surface. And that has become known as the FNV model. A few people have worked on it over the years. There's a more recent paper by Christensen and Fultonson a few years ago now. And there's a contribution from Rod Rainey back in 95 as well. So what we have is we have the equations for force supplied to a column shown on the screen. F prime is a term to be integrated all the way up from the seabed to the free surface, so from minus d to eta. And it contains within it the usual Morrison inertia term, 2 du by dt, where u is a horizontal velocity, and a couple of extra terms, which are convective derivative type terms. And the FNV model contributed the F psi term, underlined in red, which is a local property, it's local forcing close to the free surface of the horizontal velocity u squared du by dt. And it's all of these terms that I wish to calculate in a very efficient, robust manner. Okay, so the depth integral term, the term in blue, needs to be integrated up the column. And the point load obviously is applied to the free surface. Now, the difficulty with most of this is that we can measure what the free surface is doing very easily. You just stick a wave gauge in the tank and measure eta and then d eta by dt and anything you want from that. But it's actually quite difficult experimentally to measure internal wave kinematics. It can be done, but it's expensive and time consuming. And it's relatively computationally intensive to work them out below the free surface. And apparently, in order to work out the integral of f prime, I need to do a depth integral. So that's the point of the work that Tim Tan and I did. We're trying to eliminate the need for that depth integral term. Okay, that's the answer we came up with, and I don't worry about it. It looks horribly complicated, but the point is it is simply properties written at the free surface. So the depth integral is effectively done analytically. And I'd like to explain how that's done. Okay, so we've got two pictures here. The picture on the left is completely undisturbed. The column is in the middle of the domain. And I've shaded in blue the patch of water beyond the column. A picture on the right shows flow past the column associated with a wave disturbance propagating by. So U of Z distributed vertically drives eta of x of t. Now that's really important because I can use mass conservation. Any fluid that goes in past the column into the right-hand part of the domain, any U is automatically directly associated with motion of the free surface. If you push volume in, the only place it can go is move the surface up and down beyond that point. So a depth integral of U dz is related to the motion of the free surface beyond by simple mass conservation. What goes in one way must come out somewhere else. And that is the key to what we've done. It's a very, very simple property, but it turns out to be very useful because we know a lot about what the surface is doing. We know much less about what the detailed structure of U. So the integral of U dz is equal to d by dt of, so it's the vertical velocity of the free surface, essentially. We don't actually want the integral of U, we want the integral of du by dt, so the fluid acceleration, or we simply differentiate the equation on the left. So d by dt of the integral of U dz is the term I actually want, du by dt dz integrated vertically, plus an extra correction term. And that is simply the vertical acceleration of the surface integrated from the column out to plus infinity to capture all the wave field. And this simple transformation seems to pass people by. And it's really the key to doing these sort of calculations in an extremely rapid manner. Okay, so in principle, we can do this transformation. We know a lot about the surface, so I'm going to write the surface as eta in the middle of the screen. Eta is equal to eta 1. That's just linear. So if the linear surface is A cos omega t, that would be that term. Then there's some second order. The second order term, which is A squared cos 2 omega t. And the third order term, which is A3 cos A cubed cos 3 omega t. And those are the well-known Stokes-bound harmonics. They make crests and troughs, different shapes and so on. But their structure is very well understood. And if you look at the narrow-banded approximation, don't worry about the constants. We've got eta 2 is just the shape of this double frequency contribution is equal to eta 1 squared minus eta 1 Hilbert squared. Who knows what a Hilbert transform is? As a few of my students do anyway. If you start off with cos omega t, you take the Hilbert transform, you simply get sine omega t. It phase shifts everything by 90 degrees. The great advantage with the Hilbert transform is a one-line command in MATLAB. So if you look at eta 1 squared minus eta 1 Hilbert squared, that's cos squared minus sine squared. For those who can remember their school trigonometry, cos squared minus sine squared is cos 2. So by simply doing that operator, eta 1 squared minus eta 1 Hilbert squared, I get a second order term. I get my right second order term. If I want the third order term, nobody will be able to remember cos 3 omega t written in terms of cos omega t cubed and so on, but it's actually written there. So if I know the linear motion of the surface via this simple transform, I can create all the bound harmonic structure that my wave field will have as far as the surface is concerned. So it's a very, very helpful, very efficient way of representing the harmonics. Now, if you go back to the top equation, I need the integral along the surface of the double derivative, so the fluid acceleration in time. So that's what I've written on the bottom equation on the left. That's simply minus omega squared a cos omega t for the linear term. Double frequency term oscillates twice as fast, so I get 2 omega squared. Triple frequency term oscillates 3 times as fast, so I get 3 omega squared, omega p squared. But then I do my integral along the surface, which is equivalent to dividing by the appropriate wave number. And the wave number of the double frequency term is 2k. And for the triple frequency term, 3k. So when I do that division, I get the term on the extreme right-hand side, eta 1 plus 2 eta 2 plus 3 eta 3. And that's it. That's basically the answer. Everything's phase shifted by 90 degrees, but as I said, that's trivial. So the really nice thing about this is that my nasty depth integral that I would have to solve numerically in general, I've been able to transform into a term that simply runs along the surface, and I can approximate all the terms, all the individual building blocks within that term. So that's the key to what we call TFNV, it's transformation of the FNV model. This is the really important point. If you take nothing away from my talk, apart from, try and remember this slide, we've done a neat transformation of the depth integral into a free surface term, but we're only treating the Morrison linear inertia term, what is usually called linear anyway. It's certainly linear in U, because that's where I started, but it's not linear in the free surface motion. U and eta are not equivalent in this sense. U contains significant nonlinear contributions from the nonlinear free surface. It's only linear in the sense that I simply integrate U up the stick. So much of the ringing load arises from what's usually called the Morrison linear inertia term. And this is a new identification. The reason it matters is this final point, that if you want third order excitation, you must have third order structure in your solution. And the DNV guidelines for calculating ringing say you need a second order model. That is simply wrong. There's terms missing. So the standard needs to be revised. Whether or not you do it via my horizontal integral, I don't care, but you need U accurate to at least third order in the wave properties in order to get the right forcing. So that's the dominant physics of the problem. We've been able to transform depth integral into a horizontal integral and do that bit analytically. How do we test any of this? Well, we go to a very accurate kinematics code or wave evolution code that was designed and built by Harry Bingham's group in Technical University of Denmark. Christine is in the audience. She knows Harry very well, I'm sure. Extremely smart mathematician. It's a beautiful code. It's extremely robust. It's very hard to break the code, which for a wave evolution scheme is quite an achievement. Its properties don't matter, but we've used it to go to infer internal kinematics so we can test our algorithms. I'll show you a few pictures like this. I'll go through them very quickly. We have an equation at the top that I'm trying to model, and I'm going to compare the first term, which is will be a numerical depth integral, to the various approximations in terms of my horizontal free surface formulations. The column on the left is finite depth, so it's KD about 1, so it's appropriate for a fixed offshore wind turbine. KD 3 would be a big concrete platform in deep water in the northern North Sea. So we have in the top panels, the top pictures, the black curve is the surface elevation time history, and then the colored curves are different methods of approximating the various forces that come out. So the first thing I'm going to do is compare the numerical integral over depth with a numerical integral horizontally along the free surface. And so that's the top. I mean, basically the green line is an approximation, the red line is another free surface approximation, and the purple underneath everything is the exact numerical depth integral. You can see the top lines match really nicely. Then we've looked at the horizontal integral minus the vertical integral as an error. So the error is about 3% of the peak force. And then the final one is to do the horizontal integral analytically to approximate that. The errors in that approximation are even smaller. So essentially, this validates the equation at the top. There's other terms in the depth integral. There's this u du by dx, which is sometimes called convective derivative term or convective acceleration. So it fires when there's a horizontal gradient of velocity. So it's a u du by dx, again, depth integrated. A few mathematical tricks based on unidirectional waves. Incompressibility, irrotationality connect horizontal and vertical derivatives of velocity fields. So, I mean, I'll just show you the answer, that we get out the depth integral of this term can be approximated in terms of a vertical integral of a term which is itself a derivative vertically. So that then becomes trivial. So being able to transform my unpleasant depth integral into another term which is only evaluated on the free surface. So that's a convective derivative. I can also treat Rayleigh's axial divergence term. So W is the vertical velocity in the fluid column on the right-hand side, and du by dz is the vertical gradient of horizontal velocity. Exactly the same treatment allows me to write it in a very similar way. And then the pictures below compare the numerical integral with the horizontal or the free surface forms. Again, they match really nicely between modeling and the integration. But you might look at these and think, well, actually, the terms on the left are the top terms are the convective derivative. The bottom terms are Rayleigh's axial divergence term. When Tim produced these numerics for me, I looked at them and thought, they look suspiciously similar to me. They're almost identical, but one's the inverse of the other. So nature's being kind to us. That actually those two terms cancel out, almost exactly cancel out in realistic water depths for offshore wind turbines, which is very convenient because it's a bit messy to play with these terms. If I don't need them, I can just throw them away. That's just a comparison to show the residuals to the left. The peak force is about 10 meganewtons, so my errors are about 1%, which is acceptable, I think, for engineering use. Okay, so what we've been able to do is take the complete solution for the depth integral term, f prime, and express it completely in terms of free surface properties. The displacement of the surface eta and the horizontal and vertical velocity of the surface. So us is a horizontal velocity on the surface. Eta t is the vertical velocity of the fluid, of the free surface. And there's another term, which is w, which would be the fluid velocity on the surface vertically. So everything depth integrated gone. We've only got properties left on the free surface. A few comments on what the solutions actually look like. The dominant term is this first term in the square brackets with the terms ringed in red. At each harmonic, above linear, the FNV forces are larger relatively than the same harmonics in the incoming wave field. Actually, TFNV is as nonlinear as wave slope is, and wave slope is quite a nonlinear parameter. That's why the harmonics are quite large, why the structural vibration induced is quite important. This is just a picture to show. A picture on the left is free surface displacements, where for a reasonable wave, you might argue the second order terms just add a little bit to the crest, but they really don't matter. But if you look at the force time history, the relative significance of the fast wiggle, the second order signal, is twice as large, which is exactly what theory suggests it should be. Some comments on accuracy. This is the critical depth where the magic terms all cancel out. So we've got linear at the top of the picture on the right, to linear force time history, then the double frequency, triple frequency, quadruple and fifth order frequency. And you can see on this power spectrum on the bottom left how important the high harmonics are if I have a resonant frequency up at, say, 3 omega p, 3 FP. There's lots of energy there to drive structural dynamics. So you will use up some of your fatigue life due to this ringing excitation. That's a shallow water case. It works equally well for deep water, which is quite satisfactory. Okay, so this is the complete answer, at least 2/3 of the way to the complete answer, perhaps. The depth integral can be written in terms of motion of the free surface. So U has been transformed, U throughout the column has been transformed to eta along the surface. And the only other bits to the left are free surface velocities. So U, W, and d eta by dt. Well, we know d eta by dt because we can get it from eta. So how do I get my velocities to plug into this? And that depends, it depends exactly what you're trying to do. If I'm doing a computation of the wave field, then I will have free surface velocities as part of my normal output from the scheme. So I would then know the velocity and I can then plug them into the formula to work out loads on columns. I'll skip those. That's fine if I know the velocities, but I don't always know those velocities. Actually, the easiest thing to measure experimentally, and what I would be able to tackle if I were doing random time domain simulation just to do design statistics, then the nonlinear approximation for the free surface is what I would have available. Can I, from that, recreate the velocity field on the surface? The answer turns out to be yes. I won't go through the algebra. The equations are quite unpleasant, but Mathematica is good at algebra, better than me at algebra anyway. I can approximate the horizontal velocity on the free surface that I've labeled US Stokes, which is raft of terms, but they all contain, the first term contains eta 1, that's just my linear approximation. And then there's a term M2, which is actually a second order term. So it's eta 1 squared plus the Hilbert bracket. And then there's a third term labeled M3 at the end, which is the third harmonic contribution. That's as far as I need to go because I want third harmonics included all the way through. So that's how I can get a relationship between the free surface eta and an approximation for the horizontal velocity on that free surface. Likewise, I need the vertical velocity on the surface, or I can use the kinematic boundary condition to connect d eta by dt to the vertical velocity of the fluid. So that's trivial. Check those how accuracy they are. Well, there's the first row of figures is a comparison of US, so the horizontal velocity on the surface times the vertical velocity of the surface, numerically and from my Stokes approximation, and they match almost perfectly. The vertical velocity is compared in the bottom two panels. Again, that matches really nicely. So what this means is that if I know the free surface, I have enough information to do absolutely everything. It looks horrible, but Mathematica script you can program up in about 10 lines, as Jana will vouch because she's done it. Okay, so key point is that if I know the free surface, then I can get everything out. Now the proof of the pudding, as I say, is in the eating. Does this actually work if somebody is kind enough to go and measure forces for me in the lab? So a little bit on wave groups. Now, for those who are interested, this is a beautifully focused new wave. Symmetric wave group forming at a particular point in space and time. And you can see different color plots here. Concentrate first on the blue one. That has the maximum possible crest at the focus point. The other colors are what happens if I add on 90 degrees, 180 degrees, and 270 degrees to the phase of everything. So if you then look at, if you go from blue to, say, brown, that has put in 180 degrees. So that gives me the deepest possible trough ever associated with this concentration of energy. New wave is very, very useful. I mean, we developed it in Shell as a design wave, which gives a very, very high load on a space frame structure in the Morrison drag term. Very high horizontal velocities are associated with very tall crests. So you want as much energy to produce as much surface elevation as you can. It only lasts a few periods. It forms and then falls apart. It's great for CFD because I don't need to calculate hours and hours of random time domain simulation. I just need to calculate about 6 or 8 wave periods. It's great. It's even better experimentally because I can make a really clean wave in the tank, propagates off the paddle, goes down the tank, interacts with my structure, and then by the time any waves have scattered off the beach at the end and come back again, I've lost interest. The whole interaction has been and gone. So experimentally, it's a very nice technique. Computationally, it's a very nice technique. And as my student victims know, is something that I always make them look for in random data, which Jana referred to early on. I should say, I don't do much analysis, well, apart from maths. I don't do any statistical analysis myself these days. I have students to do it for me. And I think it's probably good for them. They're certainly better at MATLAB than I am. Okay, so we have a focus wave group here, and we're interested in extracting not only the total force time history, but all the harmonics within both the input wave field and the forces. I'm looking at the structure of those. So for those who have not been to Shenton Park, this is the wave flume that was built about, 3-4 years ago, I guess. Hugh spent a lot of his time organising the construction of it or the rebuilding of it. So the waves, we have paddles. We can either have a piston paddle, which is basically a vertical plate that oscillates horizontally. That's very good for relatively shallow water waves. And of course, the monopile problem is a fairly shallow water wave problem. We also have a bottom hinge paddle, which makes effectively shorter waves, i.e. equivalently waves on much deeper water. So here we can see waves go down the tank off the paddle. You see the paddle actually moving in the distance. They roll down the tank, and we usually have a beach at the far end to dissipate them, which does a pretty good job. Okay, so this is now putting a column in. I'm sorry about the flicker. I guess that's the interference with the lighting. Waves are coming from the bottom, propagating up the picture, and it should play again. Relative to the column diameter, the water goes up and down a heck of a long way. It goes up about 3 times the diameter. And there's a lot of local wave scattering around the column, which if you want to analyze in detail, you really do need CFD for. Fortunately, the total load can be reasonably accurately estimated with simple recipes of the form that I talked about. So the wave comes in, it scatters around the column, it gets fluid sheet run up the column, flow goes around the column, it meets at the rear stagnation point, keeps on coming back. So there's a lot of sort of recirculation and complicated local flow structure. I'll play one more time. Another advantage with the new wave is that obviously waves are scattered off this column. They go out to the walls, bounce off the walls and come back in again. But again, they come back in after the main interaction is finished. So you can do effectively open ocean experiments in a relatively narrow wave channel. Again, it's an advantage of the new wave form. Okay, so what did Jana measure? The little picture at the top of the screen is the total elevation in time for a focused new wave. And you can see that it is beautifully symmetric. Now, that is not easy to do. In fact, this is the best focused wave group I have ever seen anywhere. Well, Jana knows about paddles and how to code them up to make them do what you want to do. She knows about squirting vast amounts of silicon sealant to fill all the small gaps around the paddles, which people don't usually bother to do. That does make a considerable difference, but it is quite hard work to make it happen. So the signal is decomposed into its harmonics below, and this is a purely experimental decomposition. So the linear component is in blue. It's a nice symmetric group, tall crest, almost exactly equal troughs on either side. The double frequency term is in yellow/orange. No, so to say yellowish. The triple frequency term is in purple. There's even a fourth harmonic that's visible in green. And there's a brown term, which is the second order difference term. As a wave group, a large wave group, a large packet of energy forms, water's forced out beneath, out of the way. And that's the set down term that we often record. that is the one that's most difficult to get accurately represented in a tank for reasons that I don't have time to talk about. But these are absolutely beautiful experiments. So what do we get in terms of forces? Well, we can measure the total force time history, and in exactly in the same way as we can do decompositions to identify the individual surface elevation harmonics, you can apply the same process to measured force time histories. So you measure the peak force or the force time history with a crest focused new wave, with a 90-degree phase shifted new wave, 180 and 270 shifted new waves, and just by linear combinations of those measurements, you can extract all the harmonic structure. And you can see that from the force time history here, that we've adjusted the phases a bit so that you get a really tall linear component to t equals naught. You can see that the yellow term, which is a double frequency, doesn't peak when the linear one does. It peaks afterwards. It's delayed by 90 degrees. We've got a triple frequency and a fourth harmonic, and if we were to look, there'd be a fifth and sixth harmonic in there as well. The other term that we have is the Brown term, and that is the set associated with the set-down effect. Mean sea level is sagged as the group goes past, but remember the inertia term. The inertia term contains a d by dt in it, so that if eta dips downwards at t equals naught, let's go back a slide. At t equals naught, we have, of the Brown curve, d eta by dt is 0. We have negative values to the left of 0 and positive values to the right. So that's exactly what we see for the phasing of the Brown curve here. It is the derivative of the set-down term. So this matches what I said earlier, that the entire force time history is related to the slope of the wave, the slope of the incoming wave. They are essentially a single constant. So this is the ultimate proof of the pudding. We have a measured force time history in blue, and we have a truly linear inertia term, if I didn't consider any of the harmonics above the linear behavior, in brown. And you could argue they match, but they don't actually match very well. If we put in the second order sum and difference, the third order sum, fourth order sum, fifth order sum, you get that level of agreement. So let me just flick between these. So that's really not very good. That, as far as I'm concerned, is fantastic. So this is purely processing experimental data, but in this theme of the FNV model. So this is really beautiful validation of the theory, which I hope we'll publish soon. Okay, some conclusions. We propose a simple transformation of the well-known FNV model, which expresses the total force on a cylinder solely in terms of nonlinear kinematics on the surface. We propose a second approximation that does TFNV only in terms of the free surface displacements, which are easy to both measure and simulate numerically, very fast to simulate numerically. The new formulation shows the importance of the high harmonics because of this weighting towards high frequency. Scheme is incredibly robust. You can't break it, essentially. It's accurate and it's incredibly efficient. And that's actually really important because the guys who design offshore wind turbines want to simulate every wave this thing's going to see. They want to run 1 million waves as part of the design process. You cannot do that. You might be able to do 1,000 waves if you do CFD, but more likely 100. This process will allow you to do all 1 million. So if you want accurate loadings, both for your extremes and for your fatigue calculation, this is the route to go. It's published in a paper that came out this year in Coastal Engineering. The background for phase manipulation is in the paper that Colin Fitzgerald wrote when he was in Oxford with us. And the first idea of decomposition in terms of harmonics was published in GFM with Li Fen Chen, known to you all, and a few other suspects down the list. By the by, there is a tide/UWA connection to all of this. 18 months ago, Tim Tan and I were both we happened by coincidence to be staying in Forest Hall together. We got talking one evening, and this is what came out of that discussion. So TFNV stands for model transformed at Forest Hall with no velocities. If you like puns, anyway. Thank you very much. I'll try and answer any questions, but I would put up this picture on the top right. This is a little bit out of date now, but Australia wants to get to 41 gigawatts by 2040. That means one big turbine per day till 2040. No chance. But if we can make them cheaper and easier and more robust, then with a bit of luck, you'll get some in quite quickly. I would say, finally, if I could just make one final remark, safety for offshore wind should be entirely different set of calculations for safety for oil and gas offshore. What is the risk of offshore wind? You lose one turbine. You lose one turbine out of a field of, say, 100. I really don't care. Over the lifetime of a field, say 30 or 50 years, I don't care if you lose 10% of the turbines. You'll still make a lot of money. You'll make more money than if you over-design them so they all survive 50 years. The design standards probably are not going to reflect that, but should. What's the consequence of toppling a turbine? You spill a very small amount of gearbox oil, that's it. What's the problem of losing an oil and gas rig? Well, for a start, if it's manned, you might kill 200 people. And then you potentially pollute the whole of the ocean. Well, ask BP about that in the Gulf of Mexico. So the standards for safety should be very, very different. And I have a horrible feeling that that's not going to be reflected in what's coming in terms of standards for fixed offshore wind. But that's just my personal opinion. Cost reduction, make it work, and tolerate failure. Please do that. Then there's a chance of making it all practical. Thank you very much.
Thank you very much, Paul. We'll open up for questions. Aidan?
Thanks. Yeah, I was wondering, in terms of like, if you're implementing this in a in design, how do you factor in other, obviously, things like, are they consequential, like wave breaking or spread waves or?
Yeah, that's a good question. I mean, you probably want to bolt onto this a wave slam model to account for breaking. Actually, no, let me rephrase that. If you go the Stokes perturbation route, then you would want to do that. But if you're prepared to feed into it essentially almost discontinuous wave slopes associated with a corner forming and overturning, the whole formulation in terms of surface displacement, surface slope will work. Because when you get a corner, you get a forced discontinuity. So it gives you a kick. And I think that probably would be good enough. But that's work that I'm doing with Bath and Oxford at the moment as an extension. So that's the sort of negative, that there might be a little bit more to be added for the most extreme waves. I mean, not for fatigue, but for the most extreme ones. Directional spreading is going to help you. It's not included here. Directional spreading will reduce the efficiency that the harmonics couple into load. You'll have them in the free surface, but then at the second harmonic, you should maybe multiply by 0.9, and the third harmonic should multiply by 0.9 squared. So forcing in a spread sea is likely to be less nonlinear than forcing in a unidirectional sea. But these are fairly close to the coast, where local wave refraction may make the waves more unidirectional than they are further offshore. But it can only help.
I've got one online question, Paul. So from Ben, this develops an expression for the total force on the column. Are there any differences in how this should be mapped down the column compared to a standard Stokes stream function velocity acceleration distribution?
That's a good question. I mean, there's another bit of analysis. What I can get out is the total horizontal load, which I presented here, but you can also get the total moment about the seabed, so that we can work out the effective point of action of these loads up the column. So yes, there's an extra little building block. I just need enough time to simply do the algebra. I mean, I know how to do it. I've done bits of it, but it isn't all written up yet. But that's a good point, yes. If you're interested in the column dynamics and the geotech side as well. It isn't only base shear that matters, it's moment as well. So we can provide that.
I'm not sure if I missed it, but I did notice some of the relations have an approximate instead of an equal sign to do with them. And I'm just wondering, are those to do with the original FNV model, or is it to do with the transformation that you've done? And if so, what are the limitations of the model in that way?
The transformation between the depth integral and the horizontal integral is exact. The subsequent treatment of the horizontal terms in terms of a local Stokes expansion is the approximation. So that you notice that we have a KP in there for the peak, the wave number of the peak of the wave spectrum. So that's where the approximations come in. But we've tested numerically how good it is. So it's not exact, so I can't write an exact equal, but it is very close to exact, or at least to within engineering practice anyway. So it's that second stage particularly when I want to get kinematics on the free surface, they use a local Stokes expansion. So basically, locally, I treat it as A cos omega t, but A itself is a function of time to give me the variation of the waves in time.
Paul, or just on, is a horizontal integral exact if you consider like a infinite random C? Because you've just tested focus wave groups.
Well, the answer is yes, if you interpret, because everything that goes through the boundary, the left-hand boundary, is resolved in terms of motion of the resurface. So yes, it is an exact transformation, at least for a unidirectional problem. I mean, of course, it doesn't work for a spread C, so I can't do it. So all I can do is come up with approximate treatments of the individual harmonics in the spread C. But treating as a unidirectional C is definitely conservative.
You use the narrowband approximation in the transformation from the integral to just the surface elevation formulation. But do you know how well it would work for a less narrowbanded C?
I mean, we've run PM type, Pearson-Moskowitz type new waves, which are fairly broad-banded. It won't work perfectly, but it works adequately well, is the answer. I mean, what I would expect, if this is picked up by people, what I would expect them to do is do random time domain simulation, compatible with whatever spectrum they like to choose. And I don't think for plausible spectra there's any problem there. We can just maybe do some more experiments, but I don't think it's a big deal, actually. I mean, it's surprising how well the narrowband approximation does work. Nature's kind to us. Real spectra are not too broad.
Hey, Paul, thanks. For the FNB model, is there a simple explanation for what the point load at the surface represents?
No. I mean, I've thought about it for a long time. Rodney Taylor's thought about it for a long time. Neither of us understand it. But I'm not going to argue with Fultonson and Newman. I mean, it does seem to be there as an idealization of third-order diffraction. But exactly why and how, I don't know.
I mean, is it big? Like if you would
No. Actually, in the context of this, the third-order response is dominated by third-order contributions up the column, not the point load at the surface. Again, that's something which nobody's realized previously. I mean, I think when Nick Newman did the analysis properly, he had to invent some new mathematical functions. Have you ever heard of Weber function? I haven't.
Excellent. I think we ran out of questions. Thank you very much again, Paul. Fantastic talk and
My
great
pleasure.
discussion afterwards.
Thank you.